Hi everyone, this is Becky, and in this video we're going to do a little bit of review of properties of solutions from what we talked about last year and learn a little bit more vocab and do some practice calculations with concentration. So the goals here, we're just going to do a little review, learn some vocab for solutions, talk about why solutions form and how they form, and then look at concentration and calculating concentration. Okay, so as we talked about last year, and remember that a solution is just another term for a homogeneous mixture, which just means that it's one phase. So you look at it and it looks like it's all the same thing. Examples: air, steel, salt water, sugar water, all kinds of different things are possible here. Anything as long as it looks consistent and is made of more than one thing. And remember that solutions can be any state of matter. So you can have a solid solution like a metal alloy, like steel or bronze or brass. You can have a gas solution like air, and you can have liquid solutions as well. You can have solids dissolved in liquids. You can have liquids dissolved in liquids like ethanol dissolved in water. You can have gases dissolved in liquids, etc. Liquids dissolved, any kind of combination thereof is possible. Solutions don't have to be liquids. They can be any state of matter. Okay. So then when we think about solutions, because remember that if it's a homogeneous mixture, we have at least two things in it that aren't chemically combined. They're just in the same container. And so when we think about the things that are there, right, we have a component that we have the most of in our solution, and that component is the solvent, right? So it's the component of the solution that's present in largest amount. It's the thing that we think of as doing the dissolving, right? Whereas the solute is all other components of the mixture are considered solutes. You can have many solutes, but you only have one solvent because there's only one thing there that's present in the largest amount. Okay, so when we look at solutions, right, when we look at how solutions form, we're going to go into more detail of this later once we've done some review of intermolecular forces and bonding, but it's important to remember that solutions form, nature tends towards mixing. And the easiest way for us to think about this, or to look at nature tending towards mixing, is to look at a solution where you have no barriers to mixing. So when I have two gases. So in this case, I have my two gases that are separated by this barrier. So they're on each side over here. And when I remove the barrier, they mix together. And this happens every time, right? There is no instance, there is no case of two gases not doing this, two gases not mixing together. And the reason for this is complex, but it's that it's a lower energy state, right? So having this system where this here is what we call an ordered system. This, having these things mixed together like this, is a disordered system. This is lower energy. This is higher energy. This has to do with something called entropy, which is a component of the driving force behind why things happen the way that they do. We'll explore this more later, but it's important to think like if things can mix together, they will. It might take a long time, right? But if they can, they will. If there are barriers to overcome, like so for example, if I'm mixing together salt and water, I have to overcome the interactions between the Na and the Cl ions, and then the interactions between water molecules, and then replace them with interactions between water and sodium ions and water and chloride ions. And there's energy barriers to that, right? I have to break interactions and make interactions. And so if it's not energetically favorable there, that non-energetically favorable interaction might overcome the energetically favorable thing of them disordering, and then they don't dissolve, which is why you have some things that, for example, don't dissolve in water. But for the most part, making solutions, like this is an energetically favorable process. Nature tends towards mixing. We'll get into this more later, but I just wanted to draw your attention to the fact that if two things can mix together, if the barriers are low enough, they will. It might take a while, but they'll mix. Okay. So because we're talking about the substance that has two or more components, and the amount of each component relative to the other is different and can change, we need to think about the solution concentration, which basically just describes how much solute is there per given amount of solution. And we can do, there are so many different units that are possible here. The ones that we're going to focus on are here. So the first one, this is the one we used last year, that molar, capital italicized letter M, which means moles of solute per liter of solution, right? And then these are percent composition. So this is percent by mass. Sorry. All right, so this is grams of solute per gram of solution times 100, right? Percent by volume, VV is by volume, so this is volume of, so like liters of solute per liter of solution, again, times 100. And percent weight volume, so this is going to be grams of solute per volume of solution, again, times 100, okay? Percent sound complicated. They're actually the easiest ones to work. We're going to work with all three of these. The one that we're going to work with most commonly is this guy, and we did some practice with it last year. At the end of the video, I'm going to give you some problems to try from your textbook that will give you some practice working with all of these different types of units. Okay, so when we think about describing solution concentration, we can describe it in terms of the molarity or the quantitative way. But there's also some qualitative terms that we use to describe concentration often. If we call a solution concentrated, that just means that there's a lot of solute. Right, there's a lot of solute per given solution. And if it's dilute, that means that there's just not a lot of solvent. Solute. Sorry, so not a lot of solute. So these are relative terms. Like a solution can be relatively concentrated or relatively dilute. It doesn't really mean anything numerically. It just means, hey, there's a lot of stuff there versus, hey, there's not a lot of stuff there. Okay. You'll also hear the terms unsaturated, saturated, and supersaturated to describe solution concentration. And unsaturated just means that you can dissolve more. So more solute can be dissolved. At that temperature. Remember that solution, the amount of solute that can be dissolved in a given amount of solvent actually depends on temperature very strongly. So a solution is saturated, it contains as much solute as can be dissolved. I add more solute to the solution and it's just going to sit on the bottom. Nothing else is going to go into solution. Like the total amount of stuff in solution isn't going to change. And if it's supersaturated, that means that it contains more solute that can be dissolved. So these are unstable solutions. If you have a supersaturated solution and you look at it funny, it's going to crash out and you're going to end up with a precipitator. You're going to end up with stuff coming out of solution to form a saturated solution. But it's there. And they can form, basically you take the solute, you dissolve it at a high temperature, and then you cool it down very slowly so that it stays in solution but unstably. And remember, important to note that these terms are temperature dependent. As we all know, the amount of solute that can be dissolved depends on temperature. I can dissolve more salt in warm water than I can in cold water. Same thing here. So when we talk about a saturated solution, it's a saturated solution at 25 degrees. If we were talking about that same solution at 35 degrees, it would be unsaturated. So something to keep in mind and something to think about. Okay. When we talk about these terms, I have a question for you. Can a solution that you have be both saturated and dilute or unsaturated and concentrated? All right, think about it for a second. Can I have a solution that's saturated but dilute? Well, yeah, the answer to that question is yes, I can, because all it would take would be a solution of a solute that's not particularly soluble, right? So for example, if I take like calcium carbonate we consider to be pretty insoluble. So a saturated solution of calcium carbonate contains very little calcium carbonate overall, which would make it a dilute solution that is saturated. Same thing for unsaturated and concentrated. All I would need here is a solute that's particularly soluble in that given solvent, right? So for example, thinking about sodium acetate. Sodium acetate tends to be very water soluble. So I can have an unsaturated solution of sodium acetate that contains a heck of a lot of sodium acetate. So it's a concentrated solution, but it's unsaturated because I could dissolve more of it. Those terms aren't mutually exclusive. They're relative terms to describe the solution. And you'll hear them a lot. You tend to use saturated, and we tend to talk about solutions in this way a lot, just to give us a frame of reference. Okay, so most of this was review, and notice that in this video I didn't work through any examples of calculating molarity or using percent mass composition, mass percent composition, or volume percent composition, because your textbook has many worked examples in it in sections 3.3 and 3.4 with working with molarity in these units. We also did this last year a lot, so I want you to think about these problems. So I've listed some problems here. Try them. You can check your answers in the back, but then also make sure that you're comfortable. If you're not, please come and talk to me. Please come and find me during a CNC period, and we'll go from there. Okay? All right. Thanks, guys. I'll see you in class.